Not to not. I'd say yes to that's the big number. So. There's some that are kind of questionable and some, but like. There's all that's stuff like. Well, I mean, I was.
He is now.
No, that's not. No, it doesn't. Right, that's different.
Okay, let me go over the calendar for this week and next week. So we have two kind of major topics remaining to go over. U-substitution and even odd function. We'll do that today. U-substitution is basically the undoing of chain rule from derivatives. So, but it takes a little bit more work to put things back than it is to take things apart. So we need some practice with that. Integration using long division. This is really involving, there's an integral rule for natural log, and sometimes that requires long division, and complete the square is for arc trig integrals. But after tomorrow, we should be able to cover most, if not all, pretty much most all the integral rules. And then all next week, we will do a test review. Initially, I had the non-calculator portion test to be on Thursday, but I'm going to swap it to be on Friday, so that's have an extra day to review on your own. But I do need to start the calculator portion. Now, the calculator portion, the test FRQ, it's just going to be 3 problems. I'll show you exactly what they look like. So typically students do really well on them because this, we're just going to practice through these 3 types of problems that are very common FRQ type problems on the AB exam, or on the AB portion of the exam. So that will be its own test grade, and then this non-calculator portion will be its own test grade as well. Okay. But typically students do really well on the calculator portion. So we can, this will be sometime the following week. I think like maybe the following Wednesday or Thursday. But we'll have a couple of days to practice those types of problems. All right. Help sessions. So for help sessions, I'm going to have help sessions Friday, Monday, and Tuesday for the Friday test. I know that would be nice if I could just have it a little bit closer to the test day, but my AB students are also having a test next Friday, so I'm giving them Wednesday, Thursday, and Friday, but I'm also giving you 3 days as well. But tomorrow, I'm going to starting help sessions, and then tomorrow I'll also hand out the test review. So if you want to get started looking at that test review, I'll have that for you tomorrow. All right, page 43 in your packet. So U-substitution is the reverse of the derivative chain rule. So we're going back to that first packet, the big packet. We want to look for a function and its derivative to be in the integral. So for instance, suppose our function was sine of 3x. Let's go back to chain rule. What will the derivative of sine of 3x be? Cosine 3x times 3, right? So cosine of u times u prime, cosine 3x times 3. So we know that antiderivative is just working backwards from the derivative rule. So this should make sense, right? That means the antiderivative of 3 cosine 3x must bring us back to sine of 3x. So we know that this must be true, right? 3 cosine 3x must bring us back to sine of 3x plus c. So that makes sense. But if this were the problem that we were dealing with, how do we know that that 3 would end up disappearing, right? It's a little bit harder to kind of track that. going backwards, right? I think chain rule is pretty straightforward. This is whatever times u prime, but how do we know that we need that 3 there in order for us to get back to that sine of 3x? So it's a little bit harder to kind of track backwards, like, oh, we need that 3 there. Or if we don't have that 3, what would happen? So we have this second variable, this u variable, to kind of help track what we do need as we put things back together. Okay, so so basically, what we're doing with this process, we're using a second variable to make our problem easier, to do an easier version of the problem, and it's also keeping track of the coefficients that that we need along the way as we're putting things back from the chain rule that occurred before this. So let me just run through the steps, but I think it'll make a lot more sense as we work through these examples. We're going to assign the u value to the expression inside the parentheses. That's if we realize that we can't handle this problem using an easier method, such as power rule. Okay. So just like with derivatives, we always want to consider power rule as our first option, right? I think the tendency is U-substitution. Eventually, we're going to feel like, oh, that's going to be our first option, especially if we see a complicated problem. But we always want to consider, can we handle the problem using power rule? If we can't, then U-substitution is our second option. We want to find the derivative of u. So du over dx. We're trying to get everything in terms of u. Once we do that, then we should have an easier problem. Once you have an easier problem, we can make that match with the rule that we have available to us. Then we take the antiderivative. Then we bring our answer back in terms of x. So u is going to be a temporary variable for us. It will make our problem a little bit easier to look at, a little bit easier to deal with. It'll keep track of the coefficients in our problem. But then after we do the calculus portion, then we bring everything back in terms of the original variable. So here's example 2. Integral of x times x squared plus 1 to the 15th. Now, typically, we always want to see, can we just expand this out and just solve using power rule? This is possible, but that 15 will take a long time, right? Now, if it was just x squared plus 1 to the second power, then I always just rely on just power rule. I find that's faster. Expansion doesn't take very long. Distribute. Once everything is separated, just do power rule for each term and plus c. But here, we want to explore a second option because this is too complicated of a problem to expand all the way out. So for complicated problems that power rule is not able to manage easily, then U-substitution is our second method. So when we do U-substitution, we want to look for a set of parentheses. Or if we don't see a set of parentheses, can we create a set of parentheses? Because that is usually going to be where our U value is going to lie. As problems get more complicated, you may see some problems that have multiple parentheses. And if that's the case, we may have to do a little bit of guess and check, a little trial and error to get to the point where we can make it fit into a rule that's available to us. So here, it's pretty obvious that our U value is going to be the x squared plus 1. So I want you to underline the portion inside the parentheses, and also want you to underline the dx, because these are going to be your initial expressions that you substitute. Our goal is to eventually convert these in terms of from x to u, and then we'll see what's left over, and then see if we can get it to match one of the rules that's available to us. So we're going to assign the u value to be x squared plus 1, just the portion inside the parentheses. Next step, we're going to find the derivative of u with respect to x, or with respect to whatever independent variable. In this case, our independent variable is x. Most of the time, your independent variable will be x. So your second step will be du over dx. We're finding the derivative of u with respect to x. What's x squared become? Just 2x. Okay, so this is not going to be, this is not related rates. There's no time. It's not dx over dt. It's just dx. Next step, I'm going to cross multiply. I'm going to solve for dx because I want to find a replacement for dx. So cross multiply here. I get 2x dx equals du. Solve for dx. Dx equals what? Du over 2x. Now, your initial work is just to substitute these pieces. If there's any x's left over, that'll be our next step to see, okay, can we resolve the x's? But your initial step is just get these replaced, and then we can see what's next. Okay, so the x is going to stay. I'm not replacing that yet. This whole thing can be replaced with what? U. So u to the 15th. And then dx gets replaced with du. Yeah, du over 2x. So times du over 2x. Okay, can we get the x's to go away? Yes, there's one in the numerator, one in the denominator. That's fine. But there's a leftover what? Good. So the 2's in the denominator. I'm going to push it out in front as a coefficient. Get it out of the way because we know coefficient is not going to impact my calculus process. So this, we have a nice match, right? We have a rule that can handle this. This is power rule. So this is power rule that we have. The rule is integral of u du, or u to the n du is u to the n plus 1 over n plus 1 plus c. So whatever we're dealing with here should look easier than the problem that we started with. Okay, so that's first thing. If it doesn't, then we didn't find the correct u value, or we didn't go down the right path. Second, we need to have a rule that matches exactly with the rule with the problem that we have in front of us. We cannot be creative and create new rules out of what we have. So if it doesn't match exactly with the rule that's available to us, then we don't have a rule to use. Okay, so power rule, u to the 15th becomes what? Yeah, u to the 16th over 16 plus c. Okay, so that's basically our answer, but we started with what variable? X. So we have to bring x back into our final answer. So you can put all this over 32. I just prefer my coefficient in front, but you're more than welcome to just have x squared plus 1 all over 32 if you want. Okay. Much faster than if we were to expand all of this on our own and then put everything back together. Okay, next up, example 3. X squared secant squared 2x cubed. This is too complicated for any one rule. We have a rule for secant squared, which is tangent of u plus c, right? Remember that all of our trig integrals are just working backwards from our derivative trig rules. So this is too complicated for any one rule to handle. We got to go through U-substitution. What could be our u value? Yeah. Okay, let's go through our process. Cross multiply. Solve for dx. And make your substitutions. Anything that you did not underline is going to have to be will be back in your next step. Okay, so we only are getting rid of what we've underlined. Everything else will stay. And our first priority is, can we get the x's to go away? Yes, yep. X squared above, x squared below, x squared over x squared cancels out. If the x's don't go away, it could mean one of two things. One, we didn't quite go down the right path. Or two, there's some additional work that we can do to find ways around it. But we can't move into our integral step unless the x's are resolved. Okay, I see some students pull the x's out in front, do its own power rule for x, and do a rule for u. Okay, if x's are in the problem, we can't have x's and u's be together as we move into our calculus step. The x's have to be completely resolved before we do any type of integral rule. If we're going through U-substitution. Right, there's a leftover what in front? 1/6. Once you cover up your coefficient, whatever we have in front of us should be a rule that's matches exactly that's available to us. Okay, so if it doesn't match exactly to the t, that means we don't have a rule to use. But this one we do, right? Integral of secant squared u is just tangent of u plus c. Let me just put that reminder here. We do have that rule available to us. Secant squared becomes tangent. And u is only a temporary variable, so we got to bring back what? X. Yeah. So 1/6 tangent 2x cubed plus c. Example 4, first steps, can we expand? It would be nice if we can distribute that x cubed through and rely on power rule, but order of operations doesn't allow us to distribute through a radical. So we're stuck in this form, which means our second option is U-substitution. But for U-substitution, we'd like to see a set of parentheses. Can we create a set of parentheses? Yes. Raised to the what? 1/2. Okay, I want you to try this problem. Can you work your way through to the end using the steps that we've done with the first two examples? Your u value is the expression inside the parentheses, and go from there. So my u value is 5 minus x to the fourth. My du dx is negative 4x cubed. Cross multiply, solve for dx. dx equals du over negative 4x cubed. We replace the parentheses with u, replace dx with du over negative 4x cubed. X cubed cancels out. That's a good sign. No more x's in our problem. Pull the negative 1/4 out in front. And now cover the negative 1/4 up and ask yourself, do we have a rule that matches exactly with what we have? We do, power rule. So now we go through power rule. U to the 1/2 becomes u to the 3/2 over 3/2 plus c. As soon as you do power rule, your integral and your du notation drops out. A plus c replaces that. And now you're just trying to resolve your coefficients. 3/2 in the denominator, same thing as 2/3 above. Negative 1/4 times 2/3 is negative 2/12 or negative 1/6. Make sure you bring back your original x or your original variable and then plus c. So I consider these kind of nice U-substitution problems because there's something that we can do to predict that the x's goes away nicely for us. What do you notice about the degree inside the parentheses versus the degree outside? Yeah, it's always 1 degree higher. Why is that a good sign for this process?
So when you take the derivative,
Yeah.
it's like 1 lower.
Yeah, so you know that through the derivative process, after that process, it'll match that degree. So whenever I see a degree that matches or that has that staggered degree 2 or a degree higher for the u value and degree lower for the leftover variable, that's a good sign, indicating that, okay, my u substitution will clean up nicely. Now, it doesn't mean that if we don't have that relationship, it doesn't mean that U substitution doesn't work, but it may signal that there's some additional work that we need to do to get that x's to cancel it out, because we cannot move forward with our integral process unless the x's are completely gone, especially if you're trying to do U substitution. Okay, so these are the more straightforward problems. It's nice to see you can predict things will work out cleanly just by looking at the degrees of your u value with the degree of the leftover x's. Okay, next page. Okay, example 5 is a little bit not as easy to spot. Well, first off, we look at this problem, we see that we don't have a rule that can handle this mess of a problem, right? And we can't split up and say, okay, I got a rule for secant squared, I'll do that separate from tangent to the 5th. These are being multiplied, so this is one extended problem. I can't pick off different rules that there's multiplication that's connecting them. So let's create a set of parentheses and let's see what our u value could be, because only one u value is going to work. So we know that whenever we see that shorthand exponent for trig, we can always rewrite using parentheses. So we have 2 options, right? Either our u value is tangent or our u value is secant. Right? I just want us to be able to know when we would what it would look like for us to go down the wrong path, and then be able to see, okay, this doesn't work, let me try something else. So let's say our u value was secant x. Right? Okay, because that could be a potential option. But what would the derivative of secant x be? Yeah, secant x tangent x. Is this going to match with what is left over? No, right? We need 5 tangents in order for this to cancel out. This can cancel out maybe one of the tangents, but it's not going to cancel out all 5. So we know that this is not a clean relationship. And if there's any x's left over, we're kind of stuck. We can't move forward unless all the x's are gone. So this is not going to quite fit, right? We have to at least have a pathway towards all the x's going away. So let's look at our second option, which is tangent of x. What's tangent's derivative? Secant squared. So if this is our u value, is the secant squared going to manage the leftover secants? Yes, right. So that is a better fit, right? So once you observe your derivative, you should be able to look at the problem and kind of predict, okay, is this going to match up nicely? If not, then is there another option that I can look at? So I'm underlining the pieces that I want to replace. And we're hoping the secant squared will go away once we make our substitution. Are the x's cleaning up on its own? Yes. So there is no leftover coefficient, which is fine. Again, it's always okay to have leftover coefficients. We just can't have any leftover x's. But if there's a leftover coefficient, just make sure you keep track of it, push it out in front so it doesn't get in the way of your calculus, but then keep reminding yourself, I got to include that coefficient as part of my final answer. Here, there's no coefficient. It's just u to the fifth. That's just a nice clean power rule. And don't forget, your original variable needs to be presented in your final answer. Okay, question so far. Okay. Example 6. Whenever we see an integral problem, U-substitution should not be our first option, right? We should always ask ourselves, can we handle the problem without U-substitution? Can we handle the problem using just the expansion power rule? And you may be tempted to want to try U-substitution first, but you see a bunch of parentheses in the way. But this, can we handle this without U-substitution? Right, there's nothing that's preventing us from doing it, right? The same thing as just 3 minus y over y to the 1/2 dy, right? If there's only one term in the denominator, we can split them up into individual fractions, handle them separately. These are really just two independent, smaller problems. So the reason why we keep wanting to stress that power rule expansion is the first step is because if you try to go through U-substitution, that can be handled using power rule, it's not going to work. Okay, so it's not like, oh, I can factor this problem, or I can just always do quadratic formula. Like in that circumstance, quadratic formula can handle any factoring problem, but U-substitution is not one that can handle all types of problems. Okay, so if we try to go through U-substitution, we're going to get stuck. It's not going to work out. So we always want to keep in mind, first option is expansion power rule. If I can handle it using power rule, I want to do it. If it's too complicated for power rule, then U-substitution. But you can imagine how U-substitution may be your first step here because you see a bunch of parentheses. So it makes sense to be like, okay, well, see parentheses, let me just go ahead and find my potential U value. But this is just expansion power rule. So I can split up into individual fractions. Clean each up individually. Bring all the y's up to the top. What's y over y to the 1/2? It's just, I'm just subtracting exponents, right? 1 minus 1/2 is just 1/2. No need for U-substitution. This is a clean power rule problem. I just have y's instead of x's. Okay, go through power rule for both of these terms. Add 1 to the exponent divided by that new exponent. Flip the fractions up as so that we can bring them up as a coefficient. 1/2 flip the same thing as 2 over 1. 3/2 flip something as 2/3. All right, example 7. Can we expand using power rule? that radical prevents us, right? If it was x plus 3 squared, then great, we can expand and distribute. But radical, we can't get inside that radical unless there's only one term, but there's more than one term here. So let's get a set of parentheses to show up. Okay, what could be our u value? Plus 3. Now, is this going to work out as nice as our previous problems? What's the issue? Yeah, same degree, right? This will turn out to be a constant. That x is not going to cancel out on its own. There's a way around it, but at least there's a red flag, right? That it would be easier if it was x squared plus 3, because then x squared become 2x and x will cancel out, but this is not going to cancel out, which means there's some additional work we got to do. So that's just a bit of a indication that this is a little bit more involved than our previous examples 1, 2, and 3. Okay, so u equals x plus 3. Derivative du dx equals just what? 1. Okay. Cross multiply. Dx equals du. Make your substitutions. Now that x is sticking out here, right? We cannot get that. We can't move forward unless that x is somehow replaced. But we have to find a creative way. Maybe there's a creative way that we can get x's in terms of u. And the hint is maybe I can work with this equation. Can I make a substitution? X can be equivalent to what? Good. So there is our path to making this work. U minus 3 equals x. So now this can go in for that. And we're still not ready to do power rule, but at least we have a pathway towards our problem, right? Before that x was a roadblock, but now we've cleared that roadblock. And we should be able to handle this using expansion power rule, right? We're still not ready for power rule, but if we distribute that u to the 1/2 through, we should have 2 individual problems that we can handle independently. So if I multiply bases, I add exponents. 1 plus 1/2 is 3/2. Okay, apply power rule now. U to the 3/2 becomes what? Over 5/2 minus 3u to the 3/2 over 3/2 plus c. Okay. Flip all the fractions up to the top. 5/2 becomes 2/2. 3/2 becomes 2/3. Okay, are we done?
No.
What else? Yeah, let's bring back your x's. I do want to point out some things about this problem. One is, for some reason, based off of previous assessments over the years, students tend to do pretty well if it's in terms of replacing the x's back into the problem for simpler problems. But for some reason, for these change of variable problems, students tend to forget to bring the x's back in. Maybe because students already have gone through a substitution, so they feel like they're done. But just remember, if you're going through U-substitution, your answer should not contain U at the end. You got to bring back your x's. So just just want to let you know the pattern is a lot of students would do U-sub, replace all the x's fine for the other problems, but for some reason they will leave the U here. It's a minor issue. I mean, you're losing like just 1 point, but just want to highlight that. The second issue that I see is at this stage. I see some students at this stage, they feel, okay, I have x and u, no problem. I'll just do power rule for x, do power rule for u, and then end my problem. So I see students at this stage, they'll do x squared over 2 times u to the 3/2 over 3/2 plus c. Then they bring the u back in terms of x, and then they clean it up. So we can't do power rule at this stage. Okay, I know that feels easier, but that multiplication prevents us from doing it. We got to go through a change of variable. We got to go through this full step. We cannot do power rule at this stage. Okay, let me start you off with example 8, and let's just see how far we can get. First, can we expand this? No. So U-substitution is going to be our next option. What could be our U value? 2 minus x. Now this seems even more counterintuitive, because it's like, well, how is this going to cancel out with this x? Well, we can using change of variable. So we know that there's an issue, right? This is not going to match up with this x squared in any sort of way, but we can find a way around it using change of variable. Maybe I don't have a replacement for x squared, but maybe I can do a replacement for x. What can I replace x with? Mm-hmm. Well, yes, that's right. X is 2. So this will go in for this. But there's still some work we got to do, because we got to FOIL everything out before we can even consider power rule. But at least we've gotten everything in terms of one variable. All right. Yes.
You use pen.
Huh? It's just when I do pencil, it doesn't show up as nice. So I know I should be using pencil, but just for presentation purposes, I use pen. I mean, now you can FOIL out at this stage. I'm going to, I like to have my coefficients in front, so I'm going to do negative u to the 1/2. That way, after I FOIL this out, I can just distribute the negative u to the 1/2 all at the same time, and then I can just rely on power rule for the rest of it. Okay. So make sure that we are expanding correctly. We can't distribute this through, right? You got to FOIL this out first, then distribute negative u to the 1/2, then clean up every term, and then power rule for the rest, and then bring back what variable? Bring back the x, yeah. I didn't get a chance to get to the even odd functions. So in your homework, if it's dealing with even and odd functions, go ahead and skip those. We can just push everything back. So tonight's homework, just do the problems that involve use substitution. Okay, all right, come get your phones. We're on B, right, Thursday, right?
I didn't get to 6.4. Can I just? Yeah, this event.
All right, thank you.
Thank you.
Yeah, this was like, this is surprisingly. I expedite for no, like, never do it.
Would it be possible to do my take, retake for the,
Yeah,
it's like next week?
sure. Yeah, we have a test next Friday, so just pick a day for it. And just let me know ahead of time so I can prepare.
Thank you.
Thanks.